very brief introduction to her presentation and her CV. So she had received her PhD in physics in 2005 from Physical Research Laboratory, and she had specialized in the physical implementation of quantum computation during that. And she was a postdoctoral research fellow under the Women in Science and Engineering Fellowship of University of Southern California. And after that, she joined University of Toronto, her next postdoctoral research work. And she continued her work on decoherence control. And at present, she is an associate professor in the Department of Physics, IIT Ropar. And her talk today is measurement-based quantum thermal machines. I think she'll talk more on Otto engines and its efficiency and things like that. The stage is yours now. Thank you.
Thank you. Thank you, ma'am. Thank you for the nice introduction, Professor Usha Devi. And so good morning, everybody. I hope I am audible and my screens are visible.
Yes, your screen is visible.
Okay. So I am Asoka, and today I will talk on measurement-based quantum thermal machines. So before I start my talk, I sincerely thank the organizers of QIQT. Thank you for the nice introduction, Professor Usha Devi, for this talk here. And so good morning, everybody. Want to thank I hope I am audible for organizing this conference for last few years. I think this is a very good gathering, and this is a very good platform for at least the young researchers of our country. Okay, so to on moving on, this is a outline of my talk. This is how I plan to go for the next 45 minutes. So since my talk is on quantum thermal machines, so I will first discuss very briefly, I will introduce very briefly what is quantum thermodynamics, why should we study quantum thermodynamics, and what are the topics that people are doing research in this subject. And then I will come to quantum thermal machines. And while discussing the quantum thermal machine, I will first discuss that what is the classical counterpart of it. That is, what are the classical thermal machines, and how are the quantum ones. That means how are the quantum thermal machines, they are different or they are similar to the classical counterpart, and how one can implement the atypical quantum thermal machine. Okay. So, and in the last part of my talk, then I will come to my work, which is the measurement-based quantum thermal machine. Here, I will show that how, what is the contribution of measurement in a quantum thermal machine. And I will specifically discuss this measurement-based issue for a quantum Otto engine. I will show the results for single ion, 2 ion, then 2 plus 1 ion, and also I will discuss the issue of finite time quantum thermal machines. Okay. So before I start, I'd like to say that when I was preparing this slide, I assumed that a major part of this of the audience is student or the young researchers in this field. So keeping that in mind, I have prepared my slides. So this is not in that sense, in a true sense, it is an expert talk. So I mean, the expert in the audience, please excuse me. I mean, please bear with me. Okay. And also during the talk, I mean, if you need some clarification, you can interrupt me. But it will be nice if we, take questions, or if we make the discussion at the end of the talk. Okay, so moving forward, let us first discuss about quantum thermodynamics. So what is quantum thermodynamics? Quantum thermodynamics is a subject of interest. I mean, nowadays, people are very much fascinated about quantum thermodynamics, especially in the last 2 decades, though it is not a new subject at all. So the basic ingredients of quantum thermodynamics is information theory and quantum physics. By this, I mean that if you want to study quantum thermodynamics, you have to study all these 3 subjects together: information theory, quantum physics, and thermodynamics. Without this, the study will remain incomplete. Why? I think I will explain in the next few minutes. Okay. Yeah. So, but before I jump into quantum thermodynamics, let us look back into the history little bit about the development of classical thermodynamics. Okay. Can I? Yeah. So here. Okay. So it is very, well said by Einstein about classical thermodynamics that thermodynamics is the only physical theory of universal content which I am convinced will never be overthrown with the framework of applicability of its basic concepts. Okay, so thermodynamics is a very, very well established subject, and till date it is the most consistent theory ever developed, right? And it is also said that any theory you develop, any new theory you develop, it has to be consistent with thermodynamics. Okay. So if we look back into the history, we see that the journey of thermodynamics began in the 19th century, okay, with the development of steam engine. So in the first half of 19th century, before 1850, so Carnot, Joule, Kelvin, Clausius, they actually formulated the thermodynamical laws. Okay, they wanted to explain the working of steam engine, and by that they formulated the thermodynamical laws. So at that time came the first law of thermodynamics, second law of thermodynamics, all the laws of thermodynamics. They introduced entropy, a new parameter, to define the, or to connect it with the heat flow in the system, okay, which is called the thermal entropy. Then in the second half of 19th century, if you see, I mean, with the development of kinetic theory, we got the statistical mechanics. Okay, statistical mechanics developed. So statistical mechanics, basically, it is a bottom-up approach to describe thermodynamics. Okay, so thermodynamics is basically, it is a large-scale characterization of any system, or system with some macroscopic variable. Okay, but statistical mechanics starts with the molecular level. Okay, and so it is it starts from the microscopic level, and then by the averaging of average dynamics of microscopic variables, it actually rederives the laws of thermodynamics, and it connects with the macroscopic description of thermodynamics. So it is a bottom-up approach. Okay, so this is how the development was. Now, if we move on, in 1950s, there was Shannon, who actually revisited entropy in a completely different perspective. Okay, so he introduced the concept of information, and he actually connected entropy with information as it is a quantification of information. Okay, so he called it information entropy. So we have already seen that earlier in the context of thermodynamics, we have an entropy which is called the thermal entropy, which is the second law of thermodynamics. And then we have got this Shannon's entropy, or the information entropy. Okay, so now the question comes that whether these two entropies are same. So this answer to this question we get in 1960s when Landauer's in his seminal paper. So he actually said that information is physical. What does it mean by information is physical? That means information has to be hosted or stored in some physical system, in some physical body. And we know that any physical system has to obey the law of thermodynamics. So in that sense, yes, there's two kinds of entropy, the thermal entropy and the information entropy, they are same. Okay. So Landauer, in this paper, he also said that because information is physical, so if you try to erase the information, it actually causes dissipation of it. So, for example, if you it can be calculated that if you want to erase a single bit of information, at least KBT ln2 amount of it will be dissipated. Okay, so what do we mean by erasing of information? So I mean, for the students, I mean, you know that information is nothing but it is a lack of knowledge. How much you don't know is the information. It is the information content. The more you do not know, the more is the information content. Okay, so here you can see this is a quantum state rho. Okay, so this is a mixed state. Okay, so there is half of the probability to be in the zero state and half of the probability to be in the sorry, my screen is gone. How can I pin my screen?
Okay, please try again. Share your screen.
Is it visible?
Okay, okay. Yes, yes. Please make it full screen.
Yeah, just a moment. Yes. And where is the pointer option? Can you please tell me? Because I'm not very much comfortable with Zoom.
I think it will be in your system. We cannot see it.
Okay.
No,
If you
pointer, I
go
think
there
you will.
for view options,
Sorry.
Asoka, if you go for view options and
View.
there is an annotation screen appears and then there is a pointer in that. So in your own options, in your screen, top, or I think it's top in my Zoom screen.
Sorry, ma'am, I cannot see.
Don't
I mean,
see, even if you move my mouse on the
mouse, yeah,
screen,
okay.
That
Thank you, ma'am. Yeah. Okay, so yeah, so I was talking about this quantum state rho. So this is a mixed state. So there are 50-50 probability of being in zero state or in one state. Okay, so you do not know in which state the system will be. So it has some information content. Now, if you make some state transfer process, so that if you if you give some operation such that that state, this rho now reduces to this pure state, which is 0, 0. So that means you are erasing this information. Now you have the full information. You have no lack of knowledge about the system. You definitely know that the system is in 0, 0 state. So this is called erasing of information. And through this process of erasing of information, you have dissipated this amount of it, KBT ln2. Okay. Okay. And this actually solved the very classic paradox of Maxwell-Demon. Okay, but we are not discussing that here. Okay, why it's not moving? Yeah. Okay, now by having said that information is physical, and that means information has to be stored in some physical system. So that means that yeah, and as I said, that any physical system has to obey the law of thermodynamics. So in that way, information and thermodynamics, you can see that they are related. And now if you store your information in a quantum system instead of a classical system, so now you have to obey also the quantum principle, like superposition principle, and you get the advantage of quantum correlation, right? So in this sense, information theory, quantum mechanics, and thermodynamics, they all are related. Okay, so that's why I said here, everything is connected. Okay, so everything is connected is a phrase um, from a I mean science fiction movie, science fiction series, I should say. I'm really very much fond of science fiction movies or science fiction series. Okay, so this is a question for the students. I mean, can you tell me from which movie I have taken this phrase? Everything is connected. Okay, so moving on. So what is quantum thermodynamics then? So by now you have understood that quantum thermodynamics is a study when your classical thermodynamics, which basically a study of many particles. Okay, it is a large scale dynamics, so large scale characterization of system. So when it scales down to a system of few particles. Okay, so then this quantum mechanics starts playing a major role in that case. So it is basically the study of traditional thermodynamics of many particles when it scales down to the system of a few particles. Okay, and this thought that we should study quantum thermodynamics was was boosted up little more by the miniaturization of devices. With the advancement of technology, there is a miniaturization of devices. So it is very appropriate to study quantum thermodynamics. Okay. So what happens in the quantum regime? What we do, so people generally find an equivalent first law. They also rewrite the second law in light of quantum entropies, right, which is von Neumann entropies. And there is new way of defining quantum phase transition. Okay, and newer model of thermal machines with quantum system as working fluid, which is the topic I will be focusing more in this talk. Okay. So let us redefine some of the thermodynamical parameter in the quantum regime. Okay, so the basic thermodynamic parameters are heat, work, and entropy. Right. So thermodynamics is the interplay of heat and work. So now if we try to redefine them, it goes as follows. So let us consider a quantum system described by the density matrix rho. And if the system is system Hamiltonian is H, so the average energy, which is U, so average energy can be written as this trace of rho H. Okay. Now the Hamiltonian, if you since you are working in the quantum regime, your energies are discrete. Okay. So if you write down your Hamiltonian in the spectral recomposed form, right? So here Ens are the eigenvalues and N are the eigenstate of the Hamiltonian. So then you can write your average energy which is given by this expression. Okay, summation over N, Pn, En. PNs are the occupation probabilities in a particular energy level. Okay. So from here, if you now write down the infinitesimal change in your energy, which is du, so you can write it as this. So the first term is the change in the occupation probability, and the second term is the change in the energy level. So it is En dPn plus Pn Den. And crudely speaking, here this first term, it is identified as heat, and because on this first term we do not have any control, okay, and the second term, which is Pn Den, we identify this term as work done, okay, because it is basically the variation because of the time variation of the Hamiltonian, and we have a control over the Hamiltonian, okay, so we identify this as a work done, and this is our very first law, the energy balance equation. In continuous variable regime, you can write down your heat and work as this. Okay, here, I mean, this is just an identification that rho dot is equivalent to heat and H dot is equivalent to work. And lastly, this is the second law, the Clausius statement of second law. There are many variations of second law. So this is your Clausius statement that delta S is greater than equal to dq by t. Okay. Okay, so this is a very nice pictorial depiction of what we redefined right now. Okay, so how we redefine our heat and work. So this is a pictorial representation of that. So look at the first picture. So here you can see that the energy levels are not changing. Okay, so they are at their fixed position, but the occupation probabilities are changing here. Okay, so this is actually this actually means heating or cooling of the system. And in the second picture, the picture below, you can see that the occupation probability is not changing, but the energy levels, they are actually getting closer. Okay, so that means the energy levels are changing. Okay, so this is identified as work in the system. So what are the hot issues of quantum thermodynamics? That means what people do in quantum thermodynamics. So there are, I mean, because you have seen that the subject is very interdisciplinary. It is a combination of three very interesting subjects. So that's why there are many umbrellas with which people works on in quantum thermodynamics. One of the main topic is non-equilibrium quantum thermodynamics, because it is very appropriate in quantum regime to study the quantum fluctuation relations. And in this umbrella, people what people do is it has been seen that if the system is closed, the joint occupation probability of the initial and final energy eigenstate leads to a probability distribution of what? Now the question is, can the difference between energy eigenvalues be treated as work only? Okay. So as we have defined that energy difference in energy we have identified as work. So is it only work, or heat is also there? Then the question people also explore here, that should we have not included the initial and built up coherence in the energy budget? So these are the thing people work in this non-equilibrium quantum thermodynamics. Then people also work in the area of foundation of quantum thermodynamics, like people work in foundation of quantum mechanics. Similarly, foundational issues of quantum thermodynamics people work on. So here they do not consider, to describe the dynamics of the system, they do not consider the Hamiltonian, rather they treat the dynamics with maps, different maps. Okay. And here people ask the question that given the university, given the universe is pure, can the initial state of the system we consider as pure? Is it right to consider the initial state of a system pure? Or even if the universe is mixed, can the initial state of the system be pure again? So this is one thing. And another thing people work on is a single shot quantum thermodynamics. So basically, this is related with the resource theory and work extraction. So resources are those, I mean, in a quantum system or in a quantum process, what you do not get naturally, those are your resources. So right. So like non-classicality, coherence, these are the resources. So the question is, how can these resources be used to maximize your work? Okay, or what is the maximum work that you can extract from a finite size system? Okay, so because in quantum thermodynamics, in quantum limit, the system size is small, and here this ensemble average, those things doesn't work. Like in traditional thermodynamics, so fluctuation become very important here. Okay, so and finally another topic, and this is, I think, most people work on in the subject of quantum thermodynamics, is quantum thermal machines. Okay, so which is the topic of my talk today. So without much without wasting much time, let us see how can we make one quantum thermal machine. So before discussing quantum thermal machine, let us discuss a little bit about classical thermal machine, that is our traditional heat engines. Okay, so as we know that thermodynamics is a very much fundamental subject that we have understood by now, but it is, I mean, as much fundamental a subject as it is an applied subject. And the biggest application of thermodynamics is the thermal machine. Okay, so there are two kinds of thermal machines we generally discuss about. One is heat engine, another is the refrigerators. Okay, so heat engines are basically they are systems where people extract work from a thermal environment. So here you can see a picture. It is a typical toy model of a heat engine. So here you can see that there is a system, working system, and there are two baths, hot bath and cold bath. So the system extract heat from the hot bath and then release some heat in the cold bath. Okay, and in the meantime, it also does some work. Okay, so this here the system does the work. So the work is done by the system. Okay, so this model, you can understand that it blindly follows the second law of thermodynamics. So the to formulate the scientifically this working of a heat engine, so Carnot actually gave a model. So this is the model of an idealized heat engine, which is known as Carnot engine. So here in a typical heat engine work on the basis of the discrete strokes. Okay, so the engine actually, the system actually connects with the different bath, hot bath or cold bath alternatively. Okay, so so basically in general there are 4 strokes in a heat engine. So in the Carnot engine there are 2 isothermal strokes and 2 isentropic strokes. Okay, or the adiabatic strokes. And the efficiency of Carnot engine is calculated as 1 minus T temperature of the cold bath by temperature of the hot bath. Okay, so next we discuss about a practical heat engine, which is called the Otto engine. So I could not control again. I mean, while preparing the slide, this line came to my mind: an engine called Otto. This is I was motivated by a very nice movie, recent movie by Tom Hanks, which is called A Man Called Otto. Okay, so anyway, jokes apart. So moving on. So an Otto engine it is a practical version of the steam engine, and in the Otto engine, instead of 2 isothermal stroke, there are 2 isochoric stroke. Okay, so there are 2 isochoric stroke and 2 adiabatic stroke. Okay, and so this is a classical Otto engine, typical classical Otto engine. And what is the refrigerator? Refrigerator, the heat strokes, just heat flows, and the working is just opposite of a heat engine. You can see this is a typical model of a refrigerator, where the system takes heat from a cold bath and release heat to a hot bath. And hence it is, since it is going opposite, so you have to do some work on the system. Okay. And in case of refrigerator, we calculate coefficient of performance, which is the cooling energy by work input. Okay, and it is in general it is greater than 1. Okay, so so what are the major features of thermal machines? So as we have seen that these machines usually, there is a working system which is called the working fluid in the engine, and there are 2 heat reservoirs, okay, to transform the heat into work. And generally these heat engines, these heat machines, they work in the quasi-static quasi-static limit. Okay, so they maintain the equilibrium throughout the time. Okay, and but since they work in the quasi-static limit, so actually this engine, though they are efficient, but they are powerless. Okay, so but for the engine, power is very important. So the new efficiency was calculated at the maximum power, and this was done by Novikov Chambadal. So this is also the derivation was also derived by Carjon-Alborn, and nowadays it is popularly known as Carjon-Alborn limit of efficiency, which is calculated at the maximum power. Okay, so all these machines, they are cyclic with this discrete strokes, right? And the system alternatively couples with the hot bath and cold bath. So why we need quantum thermal machines? Okay, so to exploit the quantum effect in thermodynamics, we have to make the system bath interaction in quantum domain. Okay, so for that, we may also choose that, if we want to exploit the quantum properties in the quantum thermal machines, what we can do, we can actually make the bath non-thermal, okay? And we can make it a squeezed bath, okay, with non-classical properties. Also, we can explore the non-equilibrium scenario. For that means instead of quasi-static limit, we make the machine work for a finite time. Okay, and so with this, unlike quantum classical machines, it helps us in exploiting the role of quantum correlations, coherence, and finite time dynamics of heat machines. Okay. Okay. So here are the I have make a list of what people has worked so far in the context of quantum thermal machine to harness the quantum properties, okay, or to harness the quantumness of the quantum thermal machine. So in this direction, this is the first one is the famous paper by Scully and his co-workers in 2003 in Science. So they actually argued that coherence in quantum state of the system can enhance the work output, okay, and thereby improving over the Carnot limit, okay. In another paper, PRL paper, so they have shown that the efficiency of the Otto engine can exceed the Carnot limits if you use a squeezed thermal bath, okay. Then Levy, Coleslaw, Pusdin, so very recently, they showed that quantum engines operating with coherence can generate more power than the classical stochastic thermal engine. Okay, so then in another paper, people have shown that a working fluid with 2 qubits can even generate entanglement. Okay, And entanglement also enhances the performance of quantum refrigerators. So this has been shown by paper by Linden and Popescu in PRL, and Brunner and his co-workers in PRE in 2014. Okay, so these are some. This is not a complete list, I would say, but I just tried to give a list. I mean, to my knowledge. Okay. So all these quantum thermal machines, the quantum thermal machines are in discussion in the especially in the last 2 decades. Okay, so people are fascinated about discussing this quantum thermodynamics and quantum thermal machine mostly in the last 2 decades. Okay, but it is I would say it is not new. Quantum thermal machines, even quantum thermodynamics is not a new subject. Like in quantum computation and quantum information theory, we know that now we are looking at it from a new perspective, but it is the very old idea of quantum mechanics and superposition principle. Nothing new in it, but all we are doing is looking at it, looking at the subject from a very different perspective. So similarly, quantum thermal machine is not new, and the proof is that back in 1959 there was a paper that which says that 3-level measures at heat as heat engine. Okay, by Scoville and Schulz-Dubas. Okay, so this was a PRL paper back in 1959. So here you can see there is a 3-level system here, where the ground state and the fast excited state, this transition, ground state and the upper state, this transition is connected to the hot bath, and the upper state and the intermediate state, this transition is connected to the cold bath. Okay, and they have calculated the efficiency, which is nu S, which is the watt, and this is nu P, which is the heat input to the system, and it is their efficiency is consistent with the second law of thermodynamics. Okay, so this shows that this concept of quantum thermal machine is not at all new. Okay, here I give you an incomplete list of quantum proposals on quantum thermal machines. Okay, so I mean it is not again a complete list, but you can see that there are many proposals came in the last 2 decades on quantum thermal machines, and especially people in this area work with Otto engine, quantum Otto engine. So that's why here I just give you a glimpse that in this paper Q, in this PRL paper in 2004, he first actually gave an idea that a sketch that how you can implement a quantum Otto engine. Okay, so he considered the 2-level systems, which is what connected to 2 different baths. So, and he considered all these alternative strokes. Okay, so that hot isocores, when it goes to hot isocores, so it takes heat from the hot bath, and then in the second stroke, it is detached from the hot bath, and there is an isentropic expansion of the system. So that means the system and that 2 energy level come closer. So delta 1 delta 1 becomes delta 2 now, and then again it is attached to a cold bath, and it rejects some heat in the cold bath, and then you go through the isentropic compression, and where it is an expansion. So delta 2 becomes delta 1 again. And if you calculate the efficiency, so the efficiency comes out to be 1 minus delta 2 by delta 1, and which is which complies with the Carnot efficiency. Okay. So after this proposal, and there are many paper came out on working on this quantum Otto engine. Okay, how to implement theoretically to a quantum Otto engine. So in all this theoretical proposal, basically you have seen that people mimics this discrete stroke. That is, there is a quantum system which is working as your quantum working fluid, and this working fluid, this quantum system, and there are two baths they consider, hot bath and cold bath, and it is assumed that the system alternatively connect with the two baths. Okay, so sometimes the one bath is on, another bath is off, and again another bath is switched off, and the other bath is on, switched on. Okay, so we assume that this control on the bath is possible. Okay, whereas I mean you understand that a quantum system, your tiny quantum system, it is immersed into this thermal environment. So it is actually not possible to switch on or switch off your bath at your will. Okay, so in quantum regime, switching the interaction with the ever-present bath off or on is not possible unless the bath is engineered. That is, the effect of the bath is mapped by the interaction with some other system, or the system is closed, which is just a trivial assumption. Okay, so this thought that it is not possible to switch on or switch off the bath at your will, this thought was discussed in length by Professor Kurisky and his co-workers in this article, Thermodynamics of Quantum System under Dynamic Control, where they say that in any case, for nanoscale system totally embedded in thermal baths, such system bath decoupling may not be possible, which is a very justified statement. Okay, so this was the actually starting point of our work. Okay, so this paper was very thought-provoking for us, and we thought, can we make a strategy that we mimic the discrete strokes? We still maintain the discrete strokes, but and also we use the idea of this always-on bath. Okay, so Kurisky's idea was basically always on bath. How can you implement always on bath condition? And they showed how heat engines works in the continuous model, not this discrete stroke. But our idea, our strategy was to mimic the discrete stroke, but in presence of a bath interaction for all the times. So that's why we proposed that a model which is a continuous yet discrete model. Okay, we work on this single ion quantum Otto engine with always on bath interaction. Okay, so this paper was published in 2017 in EPL. Okay, so briefly I will discuss that. So here is my model. So we considered a single ion, and we consider both the degrees of freedom of the ion, that is the electronic levels of the ion and the vibrational mode of the ion. Okay, and so they are connected with each other in a unitary manner. And this vibrational mode of the ion, so they will work as one of the baths. So I will show you how. Okay, and so this is the Hamiltonian of the system. Okay, so this electronic state of the ion, so it is driven by the electric field with Rabi frequency G, and one magnetic field is also applied. Time varying magnetic field is also applied in the direction of the quantization axis. Okay, so this is your Hamiltonian. So in addition, we consider that the interaction of both the degrees of freedom with the environment remains always on. So there is a thermal environment, thermal ambient temperature is there. Okay, and this is always on. We do not need to switch on or switch it off. Okay, so my system is electronic degrees of freedom. Okay, and the hot bath is my thermal environment. So the question is, where is my cold bath? Okay, so for the cold bath, we actually use the idea of projective measurement, a selective measurement. So we project the state of the system into its ground state. Okay, and this actually reduces the entropy of the system and thereby mimics the heat release. Okay, so we do a projective measurement in the ground state of the system, and so by making this measurement in the ground state, we this actually mimics the cooling of the system, and this heat is released into this vibrational mode of the system. Okay, so this is how the cold bath is mimicked here. Okay, so what are the steps? So steps are this ignition stroke or isocoric process. Okay, so here this relates to the thermalization process due to the interaction with the ambient hot bath. Then there is this expansion stroke or adiabatic process where this work is done. So from here, the magnetic field is changed from the large value BH to the smaller value BL. Okay, then the exhaust stroke, the isocoric, again, the next isocoric process here, heat released by this projective measurement. Okay, so the measurement of the electronic state in the ground state G releases the heat into the phonon mode. Okay, and then again we in the compression stroke we initialize the system, and the magnetic field is increased from again the lower value BL to the higher value BH. Okay, so here we calculate the efficiency. Okay, so efficiency versus heat graph is shown here. Okay, so here the red curve is shown here if we do not consider any measurement, and this blue curve is if we consider the measurement with measurement. Okay, so we here we have also considered here that because of measurement heat is produced, and this cost of measurement is kBT ln2. Okay, so you can calculate it, and we have taken this into consideration while calculating our efficiency. So here we have shown that this is a successful theoretical implementation of a quantum Otto engine with a always-on bath scenario, and this is a very experimentally feasible model because we do not have to switch off or switch on your thermal bath. Okay, and in this direction, after this paper, there are many papers in last few years has come up with this measurement based heat engine, and to my knowledge, with my limited knowledge, I think this was the first paper in this direction, the measurement induced thermal machines. So the features of this model was the interaction with the hot bath is always on. We do not attempt to switch it off ever. All the 4 strokes can be implemented. The measurement is post-selective, so therefore the scheme is inherently probabilistic, and the standard trap-turn architecture can be used to implement this proposal in a real experiment. Now, to move on, we extended our work for a 2-ion case. Okay, so we considered now in case place of single ion, we considered 2 ions. So here is the Hamiltonian, and here are the eigenstate of the Hamiltonian, and this E1 is the ground state, and it is the ground state if the this coupling strength J is less than 2 BL. Okay, so this is the condition. If it maintains this condition, then till then it is the ground state. And in this work, very briefly, I will state here that if we measure the system in this ground state, it works as heat engine. And if we do the measurement in the other states like E2, E3 or E4, which are not the ground state, it works as a refrigerator. Okay. Then we consider the case where there are 2 ions. There is also there is a 3rd ion. This 3rd ion, we considered it as a ancilla. So the first and 2nd ion, the first 2 ions, they are connected by this coupling strength J1, And the second ion is connected to the third ion by this coupling strength J2. So the first ion is connected to the third ion via the second ion. So the third ion is my ancillary ion. Okay, ancillary system here. Okay, rest remains the same. So here the system is my electronic states of the ion 1 and ion 2, as I mentioned, and ancilla is ion 3. So here we found that if you plot your energy eigenvalues, okay, of the two ion, okay, so with the magnetic field, you will see some level crossing. So which are the we identified as the critical point, okay, phase transition point, okay. So there are you can see that at the at these values of the magnetic field, which is J1 by 2, you get this level crossing. So in this paper, we have shown that in the domain, when the system is the magnetic field is more than this critical point, so B is more than J1 by 2, the projection in the ground state, okay, makes a 2-qubit system works as a heat engine. Okay, so this is the graph here. Also, we have shown that the efficiency is maximum at the critical point, and above the critical point, the entanglement and the efficiency go hand in hand. Okay, so we have seen that we have calculated the entanglement also, and we have seen that the at the critical point, above the critical point, the entanglement and the efficiency, they go hand in hand here. So here we have plotted this green curve represents the entanglement. We have plotted the entanglement entropy, and the red curve is the efficiency. We have plotted it with J1. Okay, when J2 is 0. So when there is no ancilla. But when there is ancilla, so in the presence of ancilla, that means J2 is not equal to 0. We have seen that there is a degradation of the efficiency, though the work and the entanglement improves. Okay, so the moral of the story is ancilla doesn't help you in improving the efficiency of the system. So in the next study, we have actually explored the finite time limit of a single ion quantum heat engine. Okay, so far we were talking about the quasi-static limit. Okay, so now we want to consider the finite time situation for the quantum Otto engine. So this work was done in collaboration with Dr. Subhangshu Dasgupta, and so the past all these works that I have discussed so far, so this was done by my student Suman. Okay, so in this study also we have seen that as the thermalization tends to complete, the efficiency goes down to Carnot limit. Okay, so in the non-adiabatic limit, I mean in the finite time limit, you can see that there is and the efficiency is more. So the reason is that in the finite time, if you do not maintain your quasi-static limit, you retain some coherence, and this is this coherence actually playing to the role in improving the efficiency. Okay. Also, we have shown here that faster adiabatic states, that means if you do not maintain your adiabaticity, so that actually gives rise to some irreversibility of quantum friction, okay, in the system. Okay. And my another student, Choyan, is now working on this kind of system. So he has done work with a 2-spin case for a quantum Otto engine. But what he has done different is that one thing is he has considered the he has introduced some anisotropy in the interaction between the 2 spins, and also he has considered a non-selective measurement. In the past work, I have considered only selective measurement. Here he has considered non-selective measurement. Okay, so this paper is published in Physical Review very recently. So basically the model is like that. So earlier we assumed that the thermal environment is my hot bath. So now here we consider this, there is the thermal the ambience, the thermal environment. I mean the ambient bath is my cold bath, not the hot bath. Okay. And the hot bath here is implemented by the measurement on a non-selective Bell basis. Okay, so basically here you do not project your system in the ground state. Okay, so basically by this non-selective measurement here, you actually heat up the system. Okay, so this hot isocodic stage is mimicked by this non-selective Bell state measurement here. So the hot bath is mimicked by this non-selective measurement, and cold bath is always on. Okay, this kind of work was also reported in this paper. Okay, not this measurement thing. And the result is the following. So though, I mean, without anisotropy, the efficiency is more, but with anisotropy, you can see that if you plot the efficiency with time, so in the shorter times, you see some oscillations. Okay, so this oscillation is due to the interference among the non-adiabatic transition. Okay, so this is weird because as you can see that as time progresses, as a system reaches the steady state, this oscillation dies. So you can take advantage of this oscillation in the shorter time. So by choosing a appropriate time, actually you can get some enhanced efficiency in presence of anisotropy. Here we can show that at a particular chosen time, your efficiency and work, this is efficiency and work, they plotted together with different values of this anisotropy. Okay, so this is this red curve is for finite time, and this blue curve is for quasi-static limit. Okay, a quasi-static limit of eta. Okay, so we can see that the efficiency and work is enhanced in the I mean, that it can be they are enhanced by with this anisotropy here at a chosen value of properly chosen value of time. Okay, so yeah. So Choyan also works in other thermal machines like Starling machines, and but this work I will not discuss here because it is not come into the umbrella of this measurement induced quantum thermal machines. So I'm already at the end of my talk. So here I have tried to give in some experimental scenario of in this direction of quantum thermal machine. So one proposal was there, a single atom heat engine in 2016 in this science paper. So here an ion is trapped in a linear Paul trap and is coupled alternatively to the hot bath and the cold reservoir. So cold reservoir is implemented by this laser cooling beam. Okay, so and but here in this paper you will see, I mean the author they themselves they have claimed that actually this this thermal energy here, it is much larger than the energy spacing of the motional degrees of freedom. So that means it is not truly in the quantum domain, it is actually in the classical domain. So you cannot say truly it is an implementation of quantum heat engine, but they tried. Okay, so in another experimental realization where they did not implemented this thermal machine, but they actually it is actually an experimental verification of Landauer's principle. Okay, but again here it was a classical concept, and it is actually a classical experiment. And in another experimental paper in 2018, there was experimental verification of Dzerzhinsky related information theoretic inequality. by a single trap time. But this paper, though it is it was by Vedros group in US, but this paper is a quantum. Actually, the experiment was done in the quantum domain, but it is not in the direction of quantum thermal machines, which is my focus in this talk. Okay. So further, I mean, what is our future goals? So we are on it. We are working now. We want to work.
That you have only 1 minute.
Yeah, sure. I'm already at the end. So we like to explore the spin chain thermodynamics in our next endeavor. Okay, so this model is more relevant to the condensed matter physics. Okay, so there are several open questions for a spin chain and several, I mean, many things to do. So if students want to work on this, they can come and join us. So this is a summary of what we did. So we basically introduced a measurement-based quantum thermal machine where measurement can replace a bath. Okay, non-selective measurement can lead to heating and work distribution. Finite time performance has been seen, and it is seen that it can be better than quasi-static one. The heat engine performs the best around quantum critical point, and it is better to avoid ancilla for the best results. So here is my team. We have a very small group, which is quantum information and technology at IIT Ropar. So Manju works on quantum synchronization, and Choyan works in quantum thermodynamics. Jatin works on spin chain quantum synchronization, and Ratnakaran is now working on this spin chain quantum thermodynamics. Manju and Choyan, they both are outgoing students, okay, and I basically work on nothing. Okay, thank you. So I am now open to questions.
Thank you, Professor Asoka. So it's a wonderful talk on this new field. And I think that resource theories generally talk about general formalism, but your work focuses on specific things. What is the important points by this work? So I think it should be interesting to our youngsters. Any questions? You may ask her for any short questions, maybe.
Thank
So
you.
I think they can write to you.
Yeah, sure. Yeah. Sorry,
Yes.
I took a little long, actually.
Oh, no, it's okay.
Sorry for that.
So any questions?
Yeah, definitely. Yeah, students are most welcome. They can even,
Yeah,
I mean, write an email.
Yeah.
Can I ask
Please.
a question? Yes. Thank
Yeah,
you.
please.
Thank you for your talk. In linear optical elements, due to heat effects like absorbing, it can refract incident rays to different directions. In nonlinear optics, imaginary part of susceptibility can absorb light and start heating. So do you have any papers, or maybe you know any papers where such effects were studied by using quantum thermal machines?
Unfortunately, I mean, to my knowledge, I mean, right now, I can't see anything.
Okay.
Yeah.
Thank you.
Sorry. Yeah.
So I wanted to ask you one general question.
Sure.
That is on when you raise the thing on measuring difference between the eigenvalues of the Hamiltonian. Is it something right for work extraction? So I had a thought that this is basically when a Hamiltonian is changing with respect to time, you have one initial measurement of one observable, h of 0, and then h of t need not commute with h of 0. So it comes under incompatible measurements, so for which you don't have joint probabilities. So do you have any comment on that? That is to interpret it as work. So this kind of a question keeps coming because measurement disturbs the system. So now if you have
Right.
incompatible measurements, initial and final are incompatible measurements. So do they have, what kind of a meaning do they have? And that is that a quantum advantage? Do you have thought, if you have thought about it, that would be good for.
Ma'am, actually, yeah. So I did not think about it, but my comment would be, I mean, this is, first of all, this is a very crude idealization. I mean, identification of work and heat here. So yeah. So in true sense, I'm not sure how much it is perfect to identify them like this. But
Yeah.
since, as I have read also in many articles, and because this Hamiltonian, it is under the control of the scientist or the experimentalist, we can control it from the outside.
Right.
It is not about measurement. At least you can control the change. So this change, it is a controllable energy change. So this controllable change in energy is identified as yeah, what? Yeah, meaningful one. Yeah. So that's all. Yeah.
Right. Okay, thank you. So if there are no other questions, let us thank Asoka once again. Thank you. And he had done